Section 3.5, Complex Zeros and the Fundamental Theorem of Algebra. The fundamental theorem of algebra, complete factorization theorem, and zeros theorem, the specifics don't really matter. What matters is altogether, it basically says this: every polynomial with complex coefficients with a degree of d has d linear complex factors. And then therefore each factor could be solved, so also has d complex zeros. So if it's an x to the fifth, that means there's going to be 5 factors and 5 zeros. So here's an x to the sixth. It means that there should be 6 factors, 6 zeros. So let's start by factoring. This is a difference of squares. So it's x to the third squared and 8 squared. So minus 8, and then x to the third plus 8. And now these are sum of cubes and difference of cubes, because this is 2 cubed and x cubed. And for sum or difference of cubes, it's ab, a squared, ab, and b squared. And the signs that go in between depend on if it's a sum or difference. So for both of these, a is x, b is 2. So this first one factors x minus 2, because it's a difference of cubes. And then x squared, multiply them together, 2x, and 2 squared is 4. Since it was a difference, you start with subtraction, and then other sign, and the last one's always positive. For the sum of cubes, it's the same thing. It's x and 2. So it's x and 2, x squared, 2x, and 2 squared is 4. Since it's a plus, now it's plus, minus, plus. So this could still factor further. We can't factor. There's nothing that multiplies before and adds to be 2, but we can do the quadratic formula to get the solutions. So if we tee this up to solve it, we get x equals 2, x equals negative 2, and then we'll have to do the quadratic formula here. Negative b plus or minus the square root of b squared minus 4ac. 4 times 1 times 4 is 16. Over 2a. A is 1, so 2. So this is the square root of negative 12. Negative 2 plus or minus, pull out the I for the negative, square root of 12 over 2. Twelve can simplify, that's 4 times 3, so we can pull out the 2's, so it's negative 2 plus or minus 2i square root of 3 over 2. And then since everything has a 2, you can cancel those out and make them all become 1's. So it's negative 1 plus or minus I square root of 3. And do the same thing, quadratic formula for this one. Negative b, so 2, positive 2, plus or minus square root of b squared minus 4ac. 4 times 1 times 4 is 16. Over 2a, 2 times 1 is 2. That looks familiar, so that's again a negative 12. Square root of negative 12. So it's the same thing, but now it's a positive 2 instead of a negative 2. So it's going to be 1 plus or minus I square root of 3. So we have x equals negative 2, x equals 1 plus or minus I squared of 3, and x equals positive 2. So these are all your answers. Find the complete factorization of all 5 zeros of the polynomial. Since it is x to the 5th, there will be 5. So you can start, if there's anything that you see that you can factor, go ahead and do that. So everything has an x, let's factor out x. Also, everything will be divided by 3, so let's take out the 3x. So we have x to the 4th plus 8x squared plus 16. So then we're looking for what, if anything, will multiply to be 16 and add to be 8, and that works to be 4 and 4. X plus 4 and x plus 4. X squared plus 4. Then, if you were to solve this, x squared plus 4, you would set it equal to 0, move the 4 over, and then you square root both sides, plus or minus. So the square root of negative 4 is 2i. So you get x equals plus or minus 2i for each of these, which means that you could factor this, x plus 2i and x minus 2i. And same thing here, x plus 2i, x minus 2i, 3x out in front. And that's completely factored. Now to find the zeros, you would solve each of these. So we'd get x equals 0. Solve this, you get x equals negative 2i. Solve this one, you get x equals positive 2i. And then we get negative 2i and positive 2i again. So we have multiplicity of 2 and multiplicity of 2. And we got 0 as an answer one time. To come up with a polynomial when you know the zeros, just write them as the factors. So if I is a 0, then x minus I is a factor. If negative I is a 0, then it would be x minus negative I, or x plus I. 2 is a 0, so x minus 2 is a factor. And negative 2 is a 0, so x minus negative, or plus 2, is a factor. So then you can FOIL them together. This would be x squared plus xi minus xi. Those will cancel out. And I times I is I squared, so this would be minus I squared. But I squared is negative 1, so that turns into plus 1. Then x minus 2 times x plus 2 would be x squared plus 2x minus 2x cancels out, minus 4. And then FOIL that together. X squared times x squared is x to the fourth. Minus 4x squared plus x squared would be minus 3x squared. Positive 1 times negative 4 is negative 4. So there's a polynomial that has all those zeros. But then it tells us that p of 3, so here's our polynomial of x, but p of 3 needs to equal 25. So let's see what we get when we plug in 3. So 3 to the fourth is 81, minus 3x squared, so that's 3 times 9, 27, minus 4. So you put that all together, you get 50. It's supposed to equal 25. It's supposed to equal 25, so it's 25 times a, which means we actually need to think of it as 50 times something equals 25. So in this case, a would equal 1/2. And that 1/2 just needs to be multiplied throughout the whole polynomial. So the simplest way to write that is that our polynomial would then be 1/2 x to the fourth minus 3x squared minus 4. You could distribute this through if you want, but you don't need to. For this example, we wanted a degree 4 polynomial with zeros of -2 and 0, but -2 has a multiplicity of 3. So there's our 4 zeros that we need. -2, -2, -2, and 0. So all of these are x minus. So really that's x plus 2 to the third times x. And you can multiply this out. X plus 2 times x plus 2 would get you x squared plus 4x plus 4 times x squared plus 2x. I'm going to skip some of the work here, but you would distribute the x squared to everything and then distribute the 2x to everything. Combine like terms and you get x to the fourth plus 6x cubed plus 12x squared plus 8x. And there's our polynomial.